Hello, my name's Will Storr. I'm one of the lecturers here at the School of Health and Life Sciences, and I'm also one of the tutors on the biopsychosocial model. This PowerPoint is a supplementary PowerPoint around the renal system. So as with the other supplementary PowerPoints I've made, this is as well as, not instead of, the original renal system PowerPoint. The original renal system PowerPoint will have a lot more information than this PowerPoint. Here I've just tried to simplify some of the processes that are happening and hopefully make it a little bit more visual, a little bit easier for you to understand. So the next thing I'd like to talk about is osmosis. So osmosis is the movement of water through a semi-permeable membrane to maintain an equilibrium. So all this is really saying is, as you can see with the picture here, the little blue molecules are water molecules. The little yellow ladder type structure in the middle, that's your semi-permeable membrane. So the water is moving through this membrane to balance things out because there's more water on one side than the other side. The little red dots, though don't look it, are going to be molecules that are too big to pass through this semi-permeable membrane. They'll be things like your big sugar molecules, your big protein molecules that are too big to move through. The water is quite small, so it's able to pass through. And by moving through, it's balancing out. So there's 4 waters on each side now, and 6 red dots on each side. So that's your equilibrium. So osmosis itself is an inert process. It'll just happen itself. It doesn't need any energy, it doesn't need any force or anything to do it. As long as there's a concentration gradient across a semi-permeable membrane, water will move. So what's a semi-permeable membrane? Something a bit more practical, something you might be able to relate to a bit better. Consider this. I'm sure you've all seen this or something very similar to this in practice. Traffic bumps in the road, traffic cones, bollards, call them what you will. So if I come driving down this road in my car, I can get to the bollards and I have to stop. I can't pass across to the other side. But the pedestrians, on the other hand, can walk across through the bollards. So that could be considered like a semi-permeable membrane. If the pedestrians are like the water molecules, they can cross from one side of the membrane to the other. And if my car is considered like a large protein, a large sugar molecule, I can't get my car past the bollards, so I cannot cross the semi-permeable membrane. What about equilibrium? What's equilibrium all about? Equilibrium is pretty much just a balance. Trying to get things equal on both sides, so you're balancing the seesaw out. So you've got the same pressure on the left as on the right, hence the seesaw's balanced, hence in equilibrium, equal both sides. Okay, the next thing I'd like to talk about is active transport. So active transport is the movement of a substance that requires energy for it to take place. So where osmosis was a passive process, you just put 2 different concentrations between a semi-permeable membrane, the water will just move itself to even things out. With active transport, you need energy to be able to get this to move. So this is not an inert passive process, this is an active process, something you've got to put a lot of energy in for it to happen. So an example of this, it could be taking a taxi. You get in the taxi, you tell the taxi where you want to go, then when you get out your taxi you have to pay. Or your Uber, I should be more up to date now, sorry. So you're paying, so that's like active transport. Or the other example, I go to the bar and order us all a drink, and the barmaid brings the drinks over. That's active, she's physically carrying the drinks from the bar to the table. I'm not sure who ordered the half though. So the main function of the kidney is filtration. It acts almost like the body's cleaning system, removes the majority of the waste products. A lot of your waste products are excreted through the kidneys. So the main function of the kidney is filtration. this filtration pretty much occurs at the level of the nephron. So what causes the filtration here? It's the pressure difference between the blood and the Bowman's capsule. So by the time your blood reaches the Bowman's capsule into the smaller arterial vessels, you're classically looking at a pressure of about 60 systolic, so like 60 millimeters of mercury. There'll be some fluid in the Bowman's capsule, so that'll exert a bit of pressure as well. The pressure of that's about 20 millimeters of mercury. By the time you consider all the other factors involved in this, classically you have a pressure difference, a pressure gradient of about 10 millimeters of mercury. So the blood pressure's pretty much 10 millimeters of mercury higher than the pressure in the Bowman's capsule. And it's this pressure which forces the filtrate from the blood into the Bowman's capsule. As you can see in the image here, you can see the red blood cells staying within the circulation of the artery, and the yellow dots representing the filtrate being pushed out into the Bowman's capsule. Another example of this here is in this little video clip. I'll just wait for it to reset fully. You can't beat a bit of the Blues Brothers. So if you can imagine the Illinois Nazis on the bridge are the filtrate. The car driving up is the blood pressure. The blood pressure's higher, so it's forcing the filtrate into the Bowman's capsule, causing them to jump off the bridge into the river. Or you may want to think of it this way. Consider the Bowman's capsule a bit like a sieve or colander. So only the filtrate will pass through into the Bowman's capsule. The bigger molecules cannot pass through, so they'll remain in the circulation. So here I'm draining my sprouts into the sink. All the water's passing through the colander, so that'd be your filtrate. But the larger molecules are staying in the circulation, as they are too big to pass through into the Bowman's capsule. And in the Bowman's capsule, not every bit of fluid is pushed out. There's only a very slight pressure difference, so you get some fluid passed out into the Bowman's capsule, but a lot of it will retain in the circulation. So here, your large molecules, your red blood cells, your white blood cells, your platelets, a lot of your big proteins will all remain in the circulatory system. Another example here, if I strain some pasta with a colander. The pasta remains in the colander, hence the big large molecules remain in the circulation, but it's the filtrate that's coming out into the Bowman's capsule for filtration. So next we'll look at how blood pressure affects filtration, glomerular filtration, in the kidney. As you've seen from the previous slide, the blood pressure has a greater pressure than the fluid in the Bowman's capsule, so that causes the filtration to occur. So here we'll consider normal blood pressure, and I'll just go back to the example I gave you last time. The car drives, they all jump off the bridge, that's your filtration. What do you think might happen with higher blood pressure? So instead of it being a normal car like that, say it was something like this driving at the bridge, what do you think might happen there? Yes, you'll get filtration because people will jump off the bridge out of the way, but I dare say it'll also damage some of the other cars on the bridge and probably push more people off the bridge. So high blood pressure can damage the kidney. This is just purely due to the force of the blood pressure. It can damage some of the very fine structures in the kidney. And also due to this higher pressure, it can force the filtrate out into the Bowman's capsule, but also some large proteins from the bloodstream that would normally stay there into the Bowman's capsule, just purely due to the pressure, the force being applied by the blood. Okay, so we'll move on to low blood pressure. So again, exactly the same example. Going back to my top example, what do you think might happen if this car drove across the bridge? As you can see, this car is much smaller, probably moving a lot slower. Yes, you probably would get some filtrate passed into the Bowman's capsule, probably not as much as you would normally. So low blood pressure will reduce filtrate produced because you just do not physically have the pressure there to force the filtrate from the blood into the Bowman's capsule. So say we said previously that the pressure difference is about 10 millimeters of mercury. So if my blood pressure is 120/80 and I'm getting 10 millimeters of mercury pressure to push fluid out into the filtrate, if my blood pressure was to say drop to 110, so it's dropped 10 millimeters of mercury, I would still produce filtrate. It's not a complete black and white relationship, it's a bit exponential. But if my blood pressure dropped, say, from 120/80 to 80/55, I dare say that drop would be enough, so there wouldn't be enough pressure to push the filtrate out into the Bowman's capsule. So you would not get any filtrate produced, hence no urine produced. So thinking of the effect of blood pressure on kidney function, on renal function, what do you think we might see in practice? Some of the most obvious signs associated with high and low blood pressure in relation to renal function. With low blood pressure, reduced urine output or no urine output, just because there isn't the pressure there to force the filtrate out into the Bowman's capsule. So if no filtrate's been pushed out into the Bowman's capsule, the kidney won't be able to produce any urine. So you might have a patient who hasn't passed urine for a considerable period of time. This will be much easier to see in a catheterized patient as a patient who's passing urine normally. Or with high blood pressure. The classic signs here, yes, you'll see the high blood pressure, the low blood pressure when you do the OBS and work out the news score, but with high blood pressure, one of the classic signs is albumin in the urine. So albumin is one of the blood proteins. And if the blood pressure is that high, it's forcing proteins into the Bowman's capsule and hence into the kidney and into the urine. You'll see it present in the urine when you dipstick it. You'll come up positive for protein. So that should alarm you that there's a potential issue there for possible high blood pressure or possible kidney damage related to that. And in both high and low blood pressure, the key factors of kidney function or kidney damage will be in the blood tests. I'm sure you've all heard of, we'll send some U's and E's. U's and E's are urea and electrolytes, and classically monitor renal function and the salts in the blood. Two of the key tests in relation to U's and E's are your creatinine and your EGFR. Creatinine is something as a byproduct of muscle metabolism and it's often excreted by the kidneys. EGFR is estimated glomerular filtration rate, so it's a calculated value based on the blood tests. So we would send some blood tests on the patient and see what things like the creatinine and EGFR came back as from these blood tests. And that will give us an idea of how well the kidneys are working. So let's look at these blood tests in a little bit more detail now. So from the previous slide, kidney function is classically measured by measuring the U's and E's, urea and electrolytes. The specific tests related to kidney function are creatinine and EGFR. In a person with an impaired kidney function, what you'll find is the creatinine will increase. The classic range for creatinine is anything from 50 to 120. This may vary from trust to trust or whichever book you read, but that's just a baseline idea of your normal range you'd expect your creatinine to sit in. So say we do a blood test on me, you did a blood test on me, yesterday and my creatinine was 100. That's fine, it's perfectly within the normal range. But say you come today and you take some blood and my creatinine's gone to 220. Because my creatinine has doubled, that's classed as an acute kidney injury. My creatinine is double the baseline. If my creatinine had gone to say 150, 160, it'd still be a degree of kidney injury, but it wouldn't be classed as fully acute. So this graph here shows how creatinine levels may increase over time. As you see, the creatinine level increases, the renal function is worsening. So somebody with a creatinine of 200 has better renal function than somebody with a creatinine of 300 or 400. Or someone with a creatinine of 300 has a better renal function than someone with a creatinine of 600. As kidney function improves, say we start some treatment and the kidney function starts to improve, you will see the creatinine then drop back down. Hopefully the aim being get the creatinine back down to baseline. So the other test in relation to kidney function would be your eGFR. As your creatinine will increase, your eGFR will decrease. So this is measuring how well the kidneys are filtering. This is calculated mathematically from the other blood results. So over time, someone with kidney impairment, renal impairment, will see the eGFR decrease. Classically, normal eGFR is classed as anything over 60. Some trusts will report eGFR as a number, others will give you greater than 60 or greater than 90. As your eGFR decreases, this means your kidneys aren't working as well. So there's some sort of impairment with your kidney's not working as well as it should. When you get to things like eGFR of less than 30, you've got some sort of severe renal impairment. Another point related to this slide is a lot of the drugs we give in hospital can have an effect on the renal function. So you need to have an idea and awareness of this. And some drugs' dosage will vary depending on renal function. Some antibiotics and things like tinzaparin and enoxaparin, the dose will vary according to renal function. So you do need to be aware of this in practice. And again, if your kidney function becomes damaged and your eGFR does drop, if your kidney function was then to improve, you would see your eGFR increasing back up to hopefully baseline. So from the Bowman's capsule, the filtrate will then pass to the proximal convoluted tubule. I know this sounds very, very complex, very complicated, but proximal just means close to, convoluted means bent, curved, shaped, say, and tubule is just like it's a little tube. So the filtrate is going to pass into this proximal convoluted tubule. Here, the filtrate that's passed out in the Bowman's capsule contains a lot of things the body still needs. It's very indiscriminate, it's just pure force, just pushing things out of the blood. So you'll have lots of glucose, lots of water, lots of ions, lots of small molecules. The body still might want these. So here, the body can reabsorb things like glucose, amino acids, ions, water. These can be actively reabsorbed here. It may be a passive process through osmosis, it may be an active process through active transport. But it's the body's way of trying to claim back some of the things it needs. So the body's saying, yes, I did give you that, but I actually want that back. Or you might want to think of it this way, the proximal convoluted tubule. A lot of the filtrate here is reabsorbed by the body as it passes through because the body wants back a lot of the things passed out in the initial filtrate. So just think about this as a recycling centre, say, and there's people picking things off the line that they want to use, they want to recycle, that they can reuse, and the body's just doing exactly the same here. It's claiming back the things it can use and things it needs. So we'll look at the function of the loop of Henle in a little bit more detail. So this image here just illustrates the loop of Henle. So you've got your Bowman's capsule, your descending limb of the loop of Henle, ascending limb, then into your collection duct. So the descending limb is the limb going down. This limb is freely permeable to water, so water will move from this via a semi-permeable membrane by osmosis. So this will remove water from the urine, making the urine more concentrate. This is because the surrounding tissues around the loop of Henle have a very high salt content. So this promotes the movement of water out of the descending limb into the nephron, the kidney tissue itself. So the water is reabsorbed by the body. The ascending limb is the limb going up over. This limb is impermeable to water, so water cannot leave the ascending limb, so no further water will be lost at this point. But this limb has ion channels, allowing the body to reabsorb some of the key ions it needs from the urine. Things like sodium, potassium, chloride, bicarbonate. These ion channels work via active transport. So for the ions to be absorbed, the kidney needs to use energy. So it needs a good supply of energy for these ion channels to work. Or you might want to think of it this way for your descending limb of your loop of Henle. Water leaves the descending limb. This movement of water is by osmosis, movement of water across a semi-permeable membrane. So the limb itself, the descending limb itself, is a semi-permeable membrane which allows water to leave the limb into the nephron. You can see here we've got a reservoir with a dam. A lot of water is leaving the reservoir, so that's like leaving via the semi-permeable membrane, but there's also a lot of water left in the reservoir. Why is this movement occurring in the kidney? This is due to a concentration gradient. So the tissues around the loop of Henle have a very high sodium, chloride, salt content. This promotes the movement of water towards the area of the higher concentration. Remember, back to equilibrium, to try and balance things out, to get it into a balance. So you might think the tissues around the loop of Henle are attracting the water towards them. Or you might want to think of it this way, again, the descending limb of the loop of Henle. Think The Price is Right. So we've got contestants here with a blue top on, that's a bit like water. The water is passing through the semi-permeable membrane, the row of seats in front of her, down to the front to join the concentration of green, the higher concentration there. So the water is basically moving like the contestants. So as I've said previously, water is absorbed from the descending limb of the loop of Henle. So let's look at it in relation to the filtrate. So if you imagine the filtrate starts as a full pint at the top of the limb, then as it moves down the limb, more and more water is taken out of the filtrate. So it passes through the loop of Henle into the nephron around this. So by the time you get to the bottom of the loop of Henle, you've lost a significant amount of water, thus making the urine more concentrated. So we'll look at this in a little bit more detail in regards to the concentration of the filtrate. So at the top of the loop descending limb, the filtrate's very dilute. There's a lot of water there and a small amount of filtrate particles. As it moves down the limb, a lot of the water is removed. So that leaves us with a very small, much smaller volume of a much stronger filtrate. So it's much more concentrated. So here you can see on the left, the pint of orange is very dilute, and the glass of orange on the right is much more concentrated, much stronger. So when you're thinking of concentration, you might want to think of it this way. I'm trying to provide it in a way that people can relate to a little bit easier. Well, I know I can. So which of these contains the most alcohol? So we've got a double whiskey there, or a pint of beer, lager, whatever you like to call it. Which one do you think contains the most alcohol? A pint of beer, lager, classically 2 units, just to simplify things. A double whiskey, 2 units again. So they both contain the same amount of alcohol. But if you look at the volume that alcohol's in, the double whiskey has the same amount of alcohol in a much smaller volume compared to the pint. So you might want to think at the top of the descending limb of the loop of Henle you have a pint. Then by the time you get to the bottom of the loop, the descending limb, you have a double whiskey, so you've lost that much volume. Then look at the concentration of the liquids here. A pint, average concentration of a pint of lager, about 4.5% alcohol by volume. Whereas compared to a whiskey, whiskey's about 40% by volume. So it's shown both have the same amount of alcohol in them, but the volume that alcohol's containing is much smaller in consideration of the whiskies compared to the pint. So we've got to the bottom of the loop of Henle. So now the only way is up, but I'll leave that for another presentation. So think of it this way, the ascending limb, the limb that's going up over now. We've come down, so now we're going back up. The ascending limb's not permeable to water, so the water won't be able to leave here. So the water's pretty much trapped now. So as you can see here, the water cannot get past the barrier. So the ascending limb's forming a barrier that the water can't escape from. So there'll be no movement of water out of the ascending limb. No matter how hard the water tries, it will not be able to leave this ascending limb. So again, think of the ascending limb of the loop of Henle. Ions can be pumped out of the ascending limb to be reabsorbed by the body. So here, the body pumps the ions out of the limb to be reabsorbed, to be reused by the body, recycled in a way, if you like. This is done by active transport, so this requires energy to happen, whereas water leaves the descending limb just purely by osmosis, in a passive way. This is active. So in a way, the ions need to get a taxi to leave the ascending limb to return to the body. So it's going to take an amount of energy to do this. So just basically to summarise what's going on in the loop of Henle. Anyone ever been paid monthly? I know I have. The first 2 weeks of the month are like your descending limb. You've got money. Money's no object. Viva Las Vegas. Spend, spend, spend. About 13 days into the month, when you suddenly realise you haven't got that much money left, you're more like the ascending limb. You're trying to claw back whatever you can, trying to save as much as you can. A bit like the ascending limb reabsorbs all the ions it can. You're trying to pull back whatever you can. So from the ascending limb of the loop of Henle, the filtrate will now pass to the distal convoluted tubule. Again, it sounds very complicated, but break it down. Distal, it's quite far from the Bowman's capsule, so it's distal. Convoluted, again, it's bent, twisted, curved type shape, and it's a tube. So this links the ascending limb to the collecting duct, where the urine will be taken down eventually to the bladder. The main function here is antidiuretic hormone, often called ADH, acts to allow the reabsorption of water. So if the body has a low blood pressure, it might release some antidiuretic hormone to reabsorb some water to help improve the blood pressure. So in a way, you can think of this almost as the body's method of saving water, recycling the water. If it doesn't need it as much, less antidiuretic hormone will be released. If the blood pressure does drop, more antidiuretic hormone will be released. So next we're going to look at ADH in a little bit more detail. Or think of it this way, ADH, antidiuretic hormone. I know there's a picture of a tap here, and hopefully that'll become clear in a moment or two. So if we turn the tap on, its tap's going to run, water's going to go down the plug hole, down to the drain. So in a way you could think of ADH as a similar function to this. If there's no ADH, the water will run. It'll run down the plug hole, down the collecting duct, into the bladder to be excreted. But if we were to turn the tap off, then no water would run. So think of ADH as a bit like your tap. If we turn the tap on, your body's going to lose water. But if we turn the tap off, if the body starts producing lots of ADH, the body's going to retain the water, so it's not going to lose as much water. And as it said here and previously, ADH specifically works on the distal convoluted tubule, So now we've looked briefly at the kidney, we're going to look at the lower renal system. So I'll relate this to my greenhouse. So here are your collecting duct. It's a bit like the guttering on the greenhouse roof here. The rainwater will hit the roof, run down into the collecting duct, into the guttering. So the urine produced by the kidney will end up in the collecting duct. From here, it will go into the ureter. This will take the urine produced down and eventually into the bladder. So the ureter is a bit like your downspout on your guttering. Your bladder, a bit like the water butt, is an area for storing the fluid until you need to excrete it. And finally, the tap on my water butt is a bit like a urethra, the tube that the urine will flow through to leave the body. I know that's a very, very overly simplified version, but hopefully it might be something people have seen and might be able to relate to a bit better than images.